In this lesson, you will learn about the most common 40 switch topologies, as well as the different loop prevention protocols and methods available on 40 switch. After completing this lesson, you should be able to achieve the objectives shown on this slide. By demonstrating competence in 40 switch topologies, you should be able to identify the topology that best suits your network design requirements. When it comes to network design, network administrators often refer to the core, distribution, and access layers described in the widely known and adopted three-layer hierarchy model. The supported 40-switch network topologies also refer to these layers when describing the roles of 40-gate and 40-switch devices. The three-layer hierarchy model can be used as a guideline for designing reliable, scalable, and cost-effective networks. It divides the network into the following layers. Core, also known as the backbone, this layer provides reliable, high-speed transport between the WAN, the Internet, and the distribution layer. The most important consideration is speed. For this reason, devices in this layer should perform mostly switching, however, routing may also be implemented. Resource-intensive tasks, such as security inspection or quality of service, QoS, classification, should be avoided. Redundancy and fault tolerance are highly recommended. Layer 2 or Layer 3 devices can be used in this layer. Distribution, also known as the smart layer, this layer aggregates traffic from the access layer switches and forwards it to the core devices. Inter-VLAN routing, security inspection, packet filtering, and other packet manipulation tasks should take place in this layer. Redundancy and fault tolerance are recommended. Layer 2 or Layer 3 devices can be used in this layer. Access, this is where you connect the endpoints, workstations, phones, access points, servers, and so on. The access layer is usually composed of Layer 2 switches and provides network connectivity to endpoints. In addition, the access layer often performs VLAN segmentation, device authentication, network access control, NAC, and QoS classification. Access layer switches usually have a high-density port configuration to reduce per port costs. Redundancy and fault tolerance are usually not a requirement. The most basic 40-switch topology involves a single 40-gate device controlling one 40-switch device. You can configure the 40-link interface as a single physical port, a link aggregation, LAG, with one or more LAG members, or a hardware or software-based switch interface. Most of the time, it's better to use a LAG because it enables you to scale easily without having to reconfigure the 40-link interface, while offering the best throughput. You can also use a physical port for your 40-link interface. You can use this option if your 40-gate is running an earlier firmware version that does not support LAGs. If your 40-gate device is running a recent 40OS version that supports LAGs, using a LAG with a single-member interface is a better option. A third option is to configure the 40-link interface to use hardware-based or software-based switch interfaces. This setup is useful when you want to connect all your switches directly to 40-gate, instead of virtual stacking them. However, using this option is recommended only for small networks, where scalability and throughput are not expected to grow over time. That is because, for every 40 switch you add to your network, you must have a port on 40-gate. In addition, when you connect multiple switches directly to 40-gate, intra-VLAN traffic from endpoints connected to different switches is also processed by 40-gate, which can lead to a bottleneck, especially if you are using a software-based switch. The topology on this slide shows 40-switch as the access layer switch and 40-gate as both the distribution device and core device. When the same device performs the core and distribution tasks, the layer in which this group of devices operates is called a collapsed core. Under this design, the network becomes a two-layer hierarchy topology. To reduce costs, you can use this topology in smaller networks that you do not expect will experience a significant increase in traffic over time. As your network grows, you can add more switches to a single 40-gate and single 40-switch topology to form a 40-switch virtual stack. You can connect additional switches using inter-switch links, ISL. Keep the first switch connected to the 40-link interface and, optionally, connect the last switch to the 40-link interface to form a ring. When you use a ring connection to connect your switch virtual stack directly to FortiGate, you must configure the 40-link interface as a lag. You must also enable the 40-link split interface setting, to instruct FortiGate to keep only one 40-link port active, link up, at a time. Other 40-link port members are inactive, link down. If the active port goes down, one of the inactive ports becomes active. When you enable 40-link split interface, management and user traffic is not affected when two or more 40-link port members connect to two different switches that aren't configured as multi-chassis link aggregation group, MC-lag peers, which is the case in this example topology. Using a ring to connect your 40-switch virtual stack provides redundancy for the 40-link connection. If the first switch is lost, the standby 40-link connection becomes active, so the rest of the switches can continue communicating with FortiGate through the last switch. You can also manage a 40-switch virtual stack from a FortiGate High Availability (HA) cluster. Both FortiGate Clustering Protocol (FGCP) Active-Passive (AP) and FGCP Active-Active (AA) modes are supported. When you add a secondary FortiGate to the topology, you must also connect the first and last 40-switch devices to that secondary FortiGate. Note that the primary FortiGate is the only device used for switch management. That is, the secondary FortiGate can be used for processing user traffic, if AA mode is enabled, but only the primary FortiGate controls the 40-switch virtual stack. 40-link split interface is enabled. As a result, out of the 4 40-link ports, only one port, the active 40-link port on the primary FortiGate, is used for switch management. The active 40-link port on the primary FortiGate is also used for processing user traffic. The other 40-link ports on the primary FortiGate are inactive, link down. Also, the ports on the secondary FortiGate, the standby 40-link ports in the topology, are not affected by the 40-link split interface setting. That is, the ports on the secondary FortiGate remain up, link up, and on standby for switch management. On an HA failover, the secondary FortiGate takes over the cluster and 40-switch virtual stack management, and like the former primary FortiGate, it will have only one active 40-link port, which is used for both switch management and user traffic. The setup shown on this slide makes sense only when MC lag is not supported by FortiSwitch. Most FortiSwitch models support MC lag. Otherwise, it's better to use MC lag and disable 40-link split interface for better throughput. Also, the topology on this slide shows a single switch that connects FortiGate to the Internet. However, you can also use a pair of 40-switch devices acting as an MC lag peer group, for redundancy purposes. Following a more hierarchical network design, you can separate the collapsed core layer into distinctive core and distribution layers by deploying a two-tier 40-switch virtual stack topology. The access switches connect to a distribution switch that aggregates the traffic from endpoints and forwards it to FortiGate for security inspection, inter-VLAN routing, and other security-related tasks. The distribution switch in this topology, and any topology using managed switches, does not perform the smart tasks described in the three-layer hierarchical model. These tasks are performed by FortiGate, which acts as the core device. Managed 40-switch devices can perform inter-VLAN routing, allowing them to handle Layer 3 traffic between specific VLANs, instead of relying on FortiGate. This reduces the FortiGate processing load and improves network performance for trusted internal traffic. The FortiGate still manages the routing configuration, but FortiSwitch executes the actual routing. The distribution switch works more like an aggregation switch because it mainly forwards traffic between access switches and FortiGate. For this reason, you should select a FortiSwitch model that can handle the network bandwidth requirements of the aggregated traffic. The existence of one distribution switch results in only a single point of failure in the switch virtual stack. You can achieve redundancy by adding another distribution switch and using MC lag. By adding a second distribution 40 switch and configuring MC lag, you can achieve redundancy across your LAN. You configure both distribution switches as MC lag peers, so the 40-gate HA cluster and access switches form lags terminating on both distribution switches. The result is that losing a distribution switch, a 40-gate device, or an uplink on the access switch, does not result in permanent service disruption. Instead, the traffic continues to be forwarded through the redundant paths. Also, the use of lags on 40-gate and access switches results in more throughput across the network. On 40-gate, make sure 40-link split interface is disabled after you finish setting up MC lag on the distribution switches. This ensures that both lag members on the primary 40-gate are active. On the distribution switches, it's recommended that you use at least 2 inter-chassis links, ICL, for redundancy. In addition, you must enable MC lag, STP aware, it's enabled by default. When MC lag, STP aware is enabled, the switch runs spanning tree protocol, STP, IEEE 802.1d, on MC lag ICL links to detect loops caused by non-ICL links between MC lag peers. You can use a dual-homed connection for an access switch, or a ring topology for multiple access switches. In a dual-homed connection, you use 2 uplinks, each connected to a different distribution switch peer. If you are using MC lag, the uplinks in a dual-homed connection operate as a lag. In a ring connection, you stack multiple switches, and then connect only the first and last switches in the stack to different distribution switch peers. Compared to a dual-home connection, a ring connection requires fewer uplinks, but provides a lower uplink capacity. This is because switches in the ring stack can use only one uplink because the redundant uplink is blocked by STP for loop prevention. The topology shown on this slide implements redundancy on the LAN only. You can deploy a second 40-switch virtual stack on the internet edge and use MC lag to achieve redundancy for your internet connection as well. You can deploy another pair of MC lag peers on the internet edge to connect your 40-gate HA cluster to the internet. By using MC lag to connect both the LAN and edge switches, you achieve a full mesh HA topology. You must connect the new MC lag peer group to 40-link interface that is not the one used for the LAN switches. That is, you must configure a second 40-link interface on 40-gate, and as a result, you will manage 2 different switch virtual stacks. 40-gate supports the management of multiple switch virtual stacks, however, you must create the second 40-link interface on the 40-gate CLI. After that, the 40-gate GUI displays both 40-link interfaces and switch virtual stacks. You can configure a second MC lag tier on a pair of access switches, to provide higher performance and redundancy to critical end devices, such as servers, or even 40-switch devices. Usually, MC lag trunks automatically form after you connect 40-switch devices together and enable MC lag, ICL on the MC lag peers. But, when you connect 2 pairs of MC lag peer groups, on the upstream MC lag peer group, the one closer to 40-gate, you must configure the ports that connect to the downstream MC lag peer group. Based on the topology shown on this slide, if you want to use MC lag trunks between the MC lag peer group formed by the distribution switch pair and the MC lag peer group formed by the access switch pair located just below, then, on the distribution switches, you must configure the ports that connect to access switch 1 and access switch 2. On the distribution switch pair, you must apply the configuration on the 40-switch CLI under the config switch auto ISL port group subsection. The topology on this slide indicates the ports that you must configure on the distribution switch pair. This slide also shows the 40-switch OS commands required for the configuration. Note that you must apply the auto ISL port group configuration on both upstream MC lag peers, each distribution switch, in this case. In addition, the auto ISL port group configuration on each switch must be identical for the MC lag trunk between the 2 MC lag peer groups to work. Except for enabling MC lag, ICL on the ICL ports that connect the distribution switch pair and the access switch pair, you don't need to apply any other configuration for the 40-link trunks and the MC lag trunk on access switch 3 to work. FortiSwitch creates these MC lag trunks automatically for you. However, you must configure the MC lag trunk for the server on both Access Switch 1 and Access Switch 2. You do this on the FortiSwitch ports page on the FortiGate GUI. Alternatively, you can run the FortiOS CLI commands shown on this slide. Note that you must apply the same configuration on both switches for the MC lag trunk for the server to work. Usually, a 1-tier or 2-tier MC lag deployment works for most networks. However, for some networks with a high number of distribution and access switches placed across different locations within a campus or large building, or networks with large amounts of intra-VLAN traffic flowing within the distribution switch pairs, you may need to deploy another MC lag peer group. In addition to the distribution switches that handle traffic destined only to FortiGate, such as inter-VLAN or Internet traffic, north-south traffic, or traffic between different distribution switch pairs, east-west traffic. The additional MC lag peer group, formed by the core switches and the topology shown on this slide, enables your network to scale more effectively when north-south and east-west traffic grows. The topology on this slide shows 3 MC lag tiers, one for each hierarchical layer: core, distribution, and access. Note that the core tasks are performed in conjunction with the core switches and the FortiGate HA cluster. In addition, like in the 2-tier MC lag deployment, you must configure the auto ISL port groups for both the MC lag trunks between the core switch pairs and the distribution switch pairs, and for the MC lag trunks between the distribution switch pairs and the access switch pairs. You can deploy a FortiGate HA cluster with members in different locations. For this setup, you usually use dedicated links to connect FortiGate HA ports. But what if you have a limited number of fiber connections between the sites? Is it possible to use the same fiber links to pass both switch management traffic and user traffic while still deploying HA and managing the switches on both sites? In the example shown on this slide, there are 2 sites. On each site, there is a FortiGate device whose lag members terminate on different FortiSwitch devices that are part of the same MC lag peer group. For the HA setup, instead of connecting the FortiGate HA ports directly using dedicated fiber links, the HA ports are connected to the local distribution FortiSwitch pair. The goal is to use the 2 fiber links between the sites to transport both management traffic and user traffic. To do this, on FortiGate, you create 2 different FortiSwitch VLANs that are used for HA traffic. Then, you assign these VLANs to the corresponding switch ports that connect the HA ports. The switch ports that connect the distribution switch MC lag pair on each site are used to carry switch management, HA heartbeat, and user traffic. If the primary FortiGate fails, the secondary FortiGate takes over the HA cluster and switch virtual stack management. Like 2-tier and 3-tier MC lag topologies, you must manually configure the auto ISL port groups for the MC lag trunk between the distribution switch pair on Site 1 and the distribution pair on Site 2. You can also manage FortiSwitch devices over a Layer 3 network that is fully routable. This is, no network address translation, NAT, is performed along the path. This is a cost-effective solution for large networks that have multiple groups of FortiSwitch devices, called islands, that are located at different sites and must be managed from a central FortiGate device without having to deploy a FortiGate device at each site. Not only do you reduce FortiGate deployment costs, but you also avoid the administrative overhead of managing additional FortiGate devices. When you manage FortiSwitch over Layer 3, FortiGate can discover FortiSwitch only after the switch starts the CAP/WAP tunnel. That is, FortiGate doesn't use FortiLink or Link Layer Discovery Protocol, LLDP, to discover the remote switches. Also, the user traffic on the islands is not sent to the switch controller, which means that the traffic must be handled by the network devices at the remote site. Also, the FortiSwitch VLANs you configure for a FortiSwitch island are used by FortiGate for configuration purposes only, and not for processing user traffic. To manage a FortiSwitch island over Layer 3, you must configure the FortiLink interface on FortiGate. Set the target 40 link interface IP address on 40 switch, or enable IP discovery through DHCP, option 138. Enable 40 link L3 mode on the 40 switch ports facing the remote 40 gate, if you are using the internal interface for 40 gate communication. For 40 gate communication, you can use the management port or the internal interface on 40 switch. The former is an out-of-band option, and the latter is an in-band option. Using the internal interface enables you to use a lag for management traffic. Using the management interface provides you with a dedicated physical port. You can use the internal interface for one 40 switch island and the management interface for another 40 switch island, however, you can't mix interface types within a single 40 switch island. You can also manage 40 switch devices over a Layer 3 network using a virtual extensible LAN, VXLAN tunnel, to create a Layer 2 overlay network. VXLAN encapsulates Layer 2 frames into VXLAN protocol packets, which can then be routed and have NAT applied, if required. Of the 40 switch devices that support VXLAN, a limited number are hardware-based VXLAN. Hardware-based 40 switch devices can also tunnel data VLANs, in addition to performing switch management. Refer to the 40 switch feature matrix to determine which models support VXLAN 40 link management and which support VLAN tunneling, also known as VLAN stacking, Q-in-Q. Network administrators often prefer to use lags and MC lags to enable redundancy and increase network bandwidth. Although you can achieve the same outcome using multiple spanning tree protocol, MSTP, and mapping VLANs to different instances, the setup is not as simple. A spanning tree sees lags and MC lags as a single logical interface. Also, lags and MC lags are considered up if at least one of their links is up. This means that changes in the state of the links in a lag or MC lag do not trigger a spanning tree topology change unless all the links in the lag or MC lag come down. In addition, in the case of an MC lag peer group, the MC lag clients see the two peers as a single switch participating in STP. The example on this slide shows 4 interconnected switches. Switch 1 and Switch 2 are MC lag peers. Switch 3 is the MC lag client. Switch 4 is connected to Switch 3 using a regular lag. STP sees the MC lag peers as a single switch, and the uplinks on Switch 3 and Switch 4 are treated as single interfaces. In the original implementation of MC lag, STP did not run on MC lag ICL trunks. In the original implementation, if you added a non-ICL link between MC lag peers, it would cause a loop in the network. The MC lag STP aware feature, which is enabled by default, was developed to address this issue. When you enable MC lag STP aware, MC lag ICL trunks participate in STP. This means that the ports on the ICL links exchange BPDUs, which allows STP to detect loops caused by non-ICL links between switches. Note that the BPDUs are not exchanged by MC lag peers in their original frame format. Instead, BPDUs are encapsulated in the MC lag control packets that are exchanged by the MC lag peers for MC lag operation. In addition, the MC lag STP aware setting is available on the 40 switch CLI only, and you can enable or disable it by running the commands shown on this slide. This slide shows an example of a potential loop caused by a non-ICL trunk between two MC lag peers. Because MC lag STP aware is enabled, STP can detect the loop, and therefore, block the alternate path formed by the non-ICL link. This slide shows the objectives that you covered in this lesson. By mastering the objectives covered in this lesson, you learned about the most common 40-switch deployments, and how STP and other loop prevention methods can be used to ensure a loop-free topology.